So, we're going to start with John Borneff, VP Development from Terrafugia. John.
Terrafugia is the flying car company. It was started by 5 MIT grads in 2006. Our mission is to make flying cars a practical reality. And we are the leader in this space, although there's some very big names that are obviously joining us in this space. We plan to revolutionize personal transportation with a vehicle we call TFX, which has vertical takeoff and landing, semi-autonomous OPV software, production in the 2025 type of time period. We plan on catalyzing the industry with Transition, our first generation vehicle that has been driven. It's been flown, it's been tested, folding wing, light sport aircraft, you need to be an LSA pilot, production early 2019. We plan to introduce a lot of the exciting technologies from TFX into early block introductions in production, such as the OPV software and hybrid electric drive in early 2019. So you sort of say, well, what's the driving market need for flying cars? Just two things. You look at an $800 billion productivity loss associated with traffic congestion, and you look at the ever-vexing problem of general aviation flight safety, of pilots flying VFR into bad weather. Those things. And you look at the emerging technologies of driverless cars, you look at ADS-B, you look at the sense and avoid and collision avoidance technology. All of those things coming together, it makes sense. So this is going to be a vehicle for the masses. Look forward to talking with each and every one of you after the session.
Next out is Alex Bracciano from, he's a co-founder of DICE.
So a few years ago, I had the incredible misfortune of working as a management consultant for about 6 months. And I had a lot of grievances with the job, of course, but by far the worst part was the constant travel, and specifically the de-icing queues at airports during the winter season. To give you a sense, when ice formed on our airplane, instead of taking off like we usually would, we would taxi to a de-icing pad, which was usually in the most godforsaken corner of the airport. We'd then hang out there for about 30 minutes until 2 trucks proceeded to spray a heated propylene glycol solution onto the surface of our airplane in order to melt the ice. This took about 15 minutes, then we taxi back to the runway, and then we could finally take off. All said and done, this process takes about 45 to 90 minutes. It costs slightly under $10K per de-icing event, and it wastes a tremendous amount of energy and chemicals. When I later found out that this happens over 500,000 times per year in the United States alone, I set out to look for a better solution. At DICE, we're developing the first ever fully electric de-icing solution for airplanes that eliminates every single drop of chemical. By doing so, we can deliver a solution that's about 50% cheaper, one that reduces de-icing times down to 10 to 20 minutes, and most importantly to us, one that completely eliminates 25 million gallons of glycol per year in the United States alone. We've been at this for about 10 months, and to date, we've been wholly funded by grants from MIT. Although we're still in the prototyping stage, we've been approached by a handful of OEMs and a few local aircraft management companies. So my name's Alex Bracciano. I'm one of the founders at DICE, and if you guys want to learn more about our venture or our technology, I'd love to catch up after.
Next out is Dale Freed, founder of ThreeDo.
Good morning. Dale Freed, I founded ThreeDo. It's a spin-out company from MIT Lincoln Lab, and thanks to Mark Bernstein being here. So as drones or flying cars become more prevalent, we have an airspace air traffic control problem. And in particular, in order to allow drones or small aircraft to fly safely, you have to make sure that you have a system where you can track and identify these flying vehicles robustly and reliably to help them avoid hitting each other, as well as if they do hit each other and they fall out of the sky, somebody's going to get hurt. So that's bad. Now, of course, we do have an air traffic control system, and it works very well, and it's extensive, and it's reliable. The problem is that it's optimized and designed for large aircraft, at least like a small Cessna type of size up to the large commercial aircraft. And also aircraft that are flying high and aircraft that are flying fast. those characteristics don't apply to the new class of commercial drones that are flying or that will become more and more prevalent. Those aircraft tend to be small. The cross-sectional areas are maybe an order of magnitude or two smaller than what our air traffic control system was designed for. Furthermore, they fly slowly. They fly on the order of the speed that you might walk or cars are driving. So disambiguation of the signal from one of these aircraft compared to clutter is difficult. And finally, they fly low, as you know. That's part of the point, right? But the problem is that they're down near buildings and trees and all that sort of thing. So we need some way to identify and to track in a reliable manner these aircraft. And as you know, you've probably heard about the gyrocopter that was able to fly 30-some miles from Pennsylvania and landed on the White House lawn a few years ago. And that happened because we couldn't track it. So what we're developing is a laser-based system where lasers with pinpoint precision allow us to find and track these small vehicles in over large areas. And we're using a new kind of detector for the light on the receive side that allows us to sweep out large areas of the sky very rapidly. I guess I better stop there. Thank you. I'd love to talk to you later.
Next out is Josh Abbott from Ecstatic.
Thank you. So my name's Josh Abbott. I'm a scientist at Ecstatic Corporation. We're located out in Marlboro, about 30 miles west of the city here. The company was founded based on work that was carried out in Christopher Shu's group here at MIT, Material Sciences. Our core technology revolves around electrodeposition of metal alloys. So we've